This is one key part of the exam. It's going to be discussing solutions as well. We've studied solutions before. We've kind of done them all throughout the different chapters. Key thing you want to keep in mind with a solution has two components. It has a solute and a solvent. That's what makes a solution. So one thing that they focus on in AP, they love the diagrams, is when you dissolve, the solvent is what does the dissolving, right? So if the solvent does the dissolving, basically the solute is what's dissolved. That's the key part of it. So the first thing that happens, there's 3 stages in dissolving, actually. So when you drop something in water, the first thing that has to happen, or anything, the solvent particles have to be spread out. That's the first thing. That process is going to be endothermic. It requires energy to move molecules away from each other. So you're basically adding energy. The other thing is you also have to spread out the solute. That's what we call H2. That process itself will also be endothermic, require a little bit of energy to spread out those molecules. And then what happens, the last part of the dissolving process is the solvent and the solute particles interact. So it's like a bond-making process. So when you're forming bonds, although it's not like covalent bonds, but bonds of attraction between like dipole and polar molecules, or a dipole and an ion, is what happens is it releases energy. And depending on whether or not the solution process will be exo or endothermic depends on the difference between the amount of energy it takes to spread both of the molecules out and the amount of energy basically released. It's exothermic when the solution actually forms. All right, one thing we focus on is prepping solutions. When we prep solutions, we have to basically, since there's a focus on lab and lab design, here's the way it works. It goes like this. It is, you take molarity times molar mass times the liters you want will always get you grams of solute. So that'll get you the grams of the solute that you mass out, that you would weigh out on a balance. I'd weigh out a certain amount of solute on a balance, and then I'm ready to mix a solution. So a quick calculation, easy thing to remember is M times MM times L will always give you grams of solute when you go to prep or make a solution. One thing that you want to do when you make a solution, they focus on glassware, is this is called a volumetric flask in chemistry. It's basically a glass flask with a special marking on it, and it's got a cap on the top of it. We use it for making solutions. So what I would do is I would add whatever I'm going to dissolve. Let's say sodium chloride. I put sodium chloride in there. Then what I do is I add the amount of water, and they're exact volumetric. Like you could have one that's 100 milliliters. You could have one that's 1,000 milliliters, and it's exactly measured volume. So the volumetric flask. So the volumetric flask is basically what is going to help you prepare a solution. That's what the best piece of glassware to make a solution in a laboratory. So you take the volumetric flask, you put the particles in there, fill it to whatever your solvent is, usually water because we make aqueous solutions. The other thing we use for dilutions is we use M1 V1 equals M2 V2. And basically what we focus on either is M2 is whatever the new molarity is going to be. So the M2 represents a new molarity if I go to dilute something. The V1, remember this is stock solution here, represents what we're starting out, what we're going to dilute. So if we go to dilute something, that's the volume that we would put like in a volumetric flask. This represents a pipette. The reason we use pipettes is it's a specific measuring device, so you can take out specific amounts of liquid, especially when you're doing a dilution, and you can use this equation to calculate the new molarity. So be aware of that. One big focus of the AP exam this year is diagrams, how things are represented. Remember when we talk about like ion dipole, which is predominantly what you're going to see when ionic compounds dissolve in water, remember that there's positive and negative sides to a water molecule. So if you look right here, the oxygen in the water molecule, it represents a negative charge, and so it will be pointed towards, in the attraction, notice the oxygens go towards the positive sodium cation in this, whereas the negative chloride ions are attracted to the positive nature of the H's in the water molecule. So the key thing is, remember, it's an ion dipole bonding, and then the positive ions like Na+ are going to be attracted, so they'll be attracted to the O side of water, to the oxygen basically, because the oxygen is more negative in the dipole. It's a negative dipole side. So since oxygen is going to be negative on this side, positive ions will be associated with it, and then the chlorine in this case will be attracted will be attracted to the positive side, or the H side of a water molecule. So if you see a diagram like this, it represents dissolving. Here you have an ionic compound dropping in solution. Notice the chloride ions are attracted to the positive side, sodium ions are attracted to the negative side, and the molecules will orient themselves around in the solution. Like dissolves like. What does that mean? They will ask you whether or not something will dissolve in something else. It all depends on intermolecular forces. They use the term miscible. Miscible means soluble, like you've ever heard that term oil and water won't mix, because oil and water aren't miscible. So polar molecules and ionic compounds will tend to dissolve in polar substances. So if something is either polar or ionic, it'll dissolve in a polar substance, and the one we care about the most often in chemistry is water. Water is very polar. Non-polar molecules will only dissolve in non-polar compounds. So that's when we say like dissolves like. If they ask you what something's more soluble in, if it's a polar compound, it'll be more soluble in water. If it's a non-polar compound, it'll be more soluble in something that's basically non-polar, some type of oil, or it could be like, for example, in chemistry, we use this a lot, carbon tetrachloride, for example, could be soluble in that. Molarity is the unit we use for chemistry for concentration. That is just moles of solute on top, liters of solution on the bottom. So here's an example of asking you to calculate the molarity of something. You have 40 grams of NaOH, or 60 grams of NaOH, the molar mass. 60 grams of NaOH, the molar mass is 40. Overall, I basically get 1.2 moles when I set it up. So I basically take grams divided by my molar mass, and I get my moles right there. Then the last step is I have to divide that by 0.500 liters. Actually, that's going to be, that's 1.5 actually, not 1.2, 1.5. So it comes out to be 1.5 divided by 0.5. The molarity of that would be 3 if that was like a multiple choice question. Molarity of the ions. Remember when you're talking about ions in solution or ion concentrations, you have to remember to use your subscripts in the calculation. So for example here, aluminum chloride is AlCl3. What does that mean? It means I have 1 Al3 plus and I have 3 Cl minus. So if I go, the molarity of this is 0.6, but they're asking me the molarity of the chloride ion, I basically have to multiply that by 3. So in that case, if it would be 1.8 would be my molarity, because I would take 0.6 multiplied by 3, so you have to pay attention to ion concentrations as far as solutions go. Electrolytes. We talked about electrolytes at the beginning of the year. Electrolyte is a substance that when you dissolve it in water, conducts an electrical current. We did this when we were testing the different compounds. An electrolyte would be if you put an ionic compound in solution, it dissolves into ions. It caused a little conductivity meter that we used in that lab to glow, so it's a real good physical property. Strong electrolytes, you should have a general idea. Strong electrolytes are going to be ionic compounds, strong acids, and strong bases. Weak electrolytes are either weak acids or weak bases. So what will happen is, since they only break up a little bit, they will only produce slight amount of ions. Therefore, what will happen will be they will only conduct a little bit of electricity. And finally, non-electrolytes basically don't break it. You have no ions. So if something produces no ions, it will not conduct any electricity, because it goes back to the idea of what an electrolyte is. All right, last thing is, earlier in the school year, we did something with Beer's Law. We did a lab with it. Beer's Law has to do with the relationship between absorbance and concentration. If you look, basically C represents concentration, which is the molecules in a sample. Remember, we were doing Gatorade with the dye molecules. The greater number of molecules you have in concentration, the less light is going to pass through, the greater your absorbance. So as concentration increases, so does absorbance. Remember, we use a spectrophotometer, which is basically a machine that shoots a beam of light through. The other parts of Beer's Law are cell length. So basically, cell length is the pathway, the distance that the light has to travel, and all the cuvettes is going to be the same. And molar absorptivity, which has to do with some molecules absorb more light than others. So if you're testing the same molecule like we did blue food coloring, you would figure out, you'd be given what molar absorptivity is. These are basically both constant because the machine, the size of the cuvette, and this. So ultimately, it's really connecting absorbance and concentration. That's really what we're doing. So if you remember in the lab, one of our focal points was you guys had to take dye and dilute it, and so you have different concentrations to make what's called the standard curve. So you have known concentrations, for example, molarity of like 0.6, I don't know if that's exactly 0.6, but or 6 micromolar right here had an absorbance of 0.7. So you tested those in the spectrophotometer. You got all the dots that represent the data point, which is concentration and versus absorbance. So you measure the absorbance. The spectrophotometer measures transmittance, which can be turned into absorbance, which you got right off there. Absorbance is listed on the Y, concentration on the X. You get a standard curve, which is actually a line. And then what you can do is if you have an unknown concentration, if you take the absorbance, like let's say the absorbance is 0.6, I trace it into there, I drop it down there, I can figure out what the unknown concentration is. If you remember this is called lambda max. Lambda max is the wavelength of light we pick to run the spectrophotometer. That's based on the highest peak. So if I'm looking for at food coloring, the food blue 1, I basically look at the maximum wavelength of maximum absorbance. So somewhere around 620 or 630 nanometers is what I would set the spectrophotometer to during the lab. The reason why this connects to solutions is because it allows us to quantify the amount of particles or how much solute is in, like we did in the Gatorade lab. So what we're able to do in the Gatorade lab is construct a standard curve by known solutions. That's you mixing dye, diluting it, measuring it. Then you basically find an unknown value, get an unknown value there, it goes over here. Then you're able to use Beer's law, because once you know the absorbance, you know the concentration, and that's how we figured out the exact amount of dye in Gatorade using a spectrophotometer. In order for a spec to work, the ones that we used in our lab, the solution also has to be a colored solution. So the solution has to have some sort of colored ion or molecule in it in order for it to be detected by the spectrophotometer. All right? Have a good evening. I will see you tomorrow.